All right, Organic Chemistry 1, Chemistry 3101. This is kind of where we left off last class, as we were talking about E2 reactions and the regioselectivity of an E2 reaction. So I'm going to go over the first few slides kind of quickly because, we covered these last class. But let's say I have an alkyl halide, like this tertiary alkyl halide right here. You see the alpha carbon is the one that has the halogen directly attached to it. Then we have two beta carbons, right? We have the beta carbon that's in blue over here, and we have this beta carbon in green. Yes, I'm aware that there's another one here, but that's identical to the one in blue. So we have two types of beta protons. We're using a non-hindered base, ethoxide. And so when we look at the possible products that can occur after abstraction of the beta proton and the formation of the pi bond, the loss of the leaving group, right? That's our E2 mechanism. We see that we have a Zaitsev product and a Hofmann product. The Zaitsev product is the more substituted of the alkenes. You can see the Zaitsev product here as a tri-substituted alkene, which is more stable than a di-substituted alkene. And so we get the Zaitsev as being the major product in this case. So in terms of regioselectivity, the reaction is more regioselective for this beta proton, the one that's highlighted in green, right? It's just selective in terms of the region of the molecule. So there we go. We defined what a regioselective reaction is, but then we said, okay, well, we can actually control whether we get the Zaitsev, the major product in when we use sodium methoxide, we can actually control whether we get the Zaitsev or the Hofmann product by choosing our base very carefully. And I said, well, take a look at this table here. And what we see is that if we have a hindered base, like T-butoxide, or you can see that we have this even more hindered base, that the more hindered the base becomes, the more of the Hofmann product we produce. Why? Because a hindered base is going to go for the low-hanging fruit, so to speak, or it's going to go to the least sterically hindered proton. Yes, abstraction of this proton that I have highlighted in yellow gives a product that is less stable, but that proton is less sterically hindered than this one here, okay, which is on a methylene as opposed to the one that's on a methyl group. And so, again, we can just select our base and we can choose which one of these two products we want to get in a higher yield. The problem with this kind of stuff, though, is that no matter what, if you look at all the scenarios, no matter what, you end up with a mixture, don't you? You always end up with a mixture. So then you have to find a way to separate those. But we'll just assume that we're good at separations and that we can do that. So again, I talked about why a sterically hindered base favors the Hofmann product, because it goes for the less sterically hindered proton. And towards the end of the last lecture, I said, besides T-butoxide or potassium T-butoxide, which we'll normally abbreviate like this, I said there's other bases that we can use, like diisopropylamine and triethylamine. You can see that why they're bases. They have a lone pair, right? We think of a Lewis base as being an electron donor, while the pair of electrons on the nitrogen of these amines can be donated. And these are very commonly used bases, diisopropylamine, triethylamine. What's great about them is that they're liquids at room temperature, so they're easy to manipulate. You know, organic chemists will usually lean towards a liquid if they can, and I'd say solid would come second, and then gas as well. Organic chemists try to avoid those at all costs, you know, using a gas in a reaction. So the last thing that we did was look at this problem here, practice the skill 7.18, predict major and minor products. And what I really want to point out is the last two problems that we did, we saw that we could use an unhindered base or we could use a hindered base, and we could control the regioselectivity of the reaction, of the E2 reaction. Remember, the whole point is we're looking at E2 reactions, and we've already covered SN2 reactions. Well, let's look at something new today in terms of stereoselectivity, right? If I had these two isomers of 2-pentene, you can see that these are stereoisomers, aren't they? Right? They're constitutional isomers, but they have a different arrangement of atoms in space, and so they are stereoisomers. So the question is this: if I have, you know, only one kind of beta proton, which is this one right here, I mean, I could draw this one here, but there's a plane of symmetry in the molecule, so it doesn't matter. But anyhow, if I was to eliminate, you know, this proton, well, since we have free rotation around this carbon-carbon bond, that means that I could end up with either the trans product or I could end up with the cis product. Now you can probably guess, and you can tell from this reaction coordinate diagram in terms of the potential energy, that the trans is going to be more stable because it's less sterically hindered. But again, we get two possible stereoisomers here. And again, I mean, there's two protons here in the methylene. And what we're going to see later on is that when you form one of the products, it would be the abstraction of one of the protons. And when you form the other one, the other stereoisomer, it would be the other proton. And that's a lot of what we're going to talk about this morning. All right. So let's talk about stereospecificity. Okay. So if you look here, it says stereoselectivity, right? Selective. What does selective mean? It means it's selective for one over the other. We have a major product and a minor product. But when I'm talking about stereospecificity, it means it's specific. We're only going to get one product. So take a look here. What if we wanted to do a dehydrohalogenation, an E2 reaction, on this compound right here? Okay, well, I can see that this carbon is the alpha carbon. It's got a bromine, so that's good. If I look at the two beta carbons, there's one here. This beta carbon that I have the yellow highlighter on, it has no protons that can be removed, so I can just forget that one. But this one here only has one proton. Okay, it's actually a stereogenic center, right? This is a stereo center right here, as is this. They're both stereo centers. And so you might think, well, based off of what you showed me on the last slide, Mr. Dion, I should be able to get a mixture of the E and the Z product. But what you find is that if you do an E2 reaction on this molecule, you only get one product, and it happens to be where the phenyl and the hydrogen are on the same side of the double bond, right? You see them over here. Okay, so we only get one possible isomer here. The other one isn't formed at all. Well, that's kind of interesting. Now, why would that be? And we're going to answer that question right now, and I'm going to teach you how to answer that question yourself, obviously. That's one of the points here, right? So again, here we have the E isomer, which is the only one formed. Okay, so this is the E product. And then we get none of the Z. Nothing. Zilch. Okay, and there's a good reason for that. I'm going to tell you the quick answer right away. Okay, just in case you're ahead of me, if you took the time to read the book before coming to class. But the bottom line is this. In order for the elimination to occur, the bromine and the hydrogen that are going to be abstract, so your leaving group and your proton that you're going to remove, they have to be all in the same plane. You see how all these three bonds that I have the yellow highlighter on, they're all in the plane of the screen or the page, whatever you're looking at, right? You see how the phenyl is coming out, the methyl's going in, right? The hydrogen's coming out, the tert-butyl's going in, but everything that I have the yellow highlighter on, they're all in the same plane, and then they have to be kind of like trans to each other. It's not actually called trans, but they have to all be in the same plane, and they have to be on opposite sides of where the carbon-carbon double bond will form. Okay, so when I do the elimination, I'll just draw, a generic base here, could be a thiouxide. When you remove this proton, you form the double bond like this. You see that the phenyl and the hydrogen are both pointing towards you. So that means they're going to end up on the same side of the molecule. You see how the methyl and the tert-butyl are both pointing away from you? Well, that means that they're going to end up on the same side of the molecule. So that's the quick and dirty answer. Well, let's take a look at it in detail now. So to rationalize, I'm just reading off this slide, to rationalize this stereospecificity, why we get specifically one product, okay, we have to look at the transition state. And what I told you is that in the transition state, the carbon hydrogen and the carbon bromine bond that are breaking have to be in the same plane as the pi bond that's forming. So this is what I was showing you in the last slide. Everything here in red that I have the yellow highlighter on, all of those atoms must lie in the same plane, and we say that they are coplanar, okay? And I'm not going to use the word coplanar a whole lot, and I'll explain why in a few minutes. What we actually use is anti-periplanar, but I'll get to that in a second. But again, they're all in the same plane. If they're not all in the same plane, let me just tell you right now that E2 reaction won't happen. It just doesn't happen at all. Zilch, zero, nothing. Just doesn't work, okay? So in order for when we have the hydrogen and the bromine coplanar, right, all in the same plane, you actually see that there's two rotamers where that can happen, okay, where they're both coplanar. We have the one here where I told you it's kind of like as if they were trans. They're not, okay? Again, we call it anti-coplanar, and I'll explain it in a second. You can see the word down here, okay? But there's another rotamer here where they're all in the same plane. But if you look at the Newman projection, okay, so if you look at the Newman projection, if you look down this carbon-carbon bond, you would see this, okay? And you would see that the bromine and the hydrogen are anti to one another. And we say that they are anti-coplanar or anti-periplanar, and I'll explain what periplanar means in a few minutes. But either way, you see that they are anti to one another, right? They're anti. You remember syn and anti and staggered and eclipsed and all that stuff. Well, they're anti to each other, okay? If we look at the other rotamer, so if you take another eyeball and you look down this carbon-carbon bond, what you see is that they're coplanar, but they're syn coplanar. They're eclipsed. Okay, now you can imagine which one of these two conformations is more stable, right? It's going to be the one that's staggered. Okay, and so in order for the elimination to occur, this is not going to work. The whole syn coplanar arrangement, it won't work. So there's only one possible rotamer, and that's why the reaction is stereospecific. Let's take a look at it in more detail. So we have the lower energy rotamer. That's going to be the preferred one. I mean, the syn coplanar one is such high energy that the elimination is only going to result from the anti-coplanar rotamer. So, you know, if you're thinking, oh man, these are fancy words, I don't like fancy words. Look, the bottom line is this. When you look at the Newman projection of your substrate that's undergoing an E2 reaction, okay, the bromine and the hydrogen, or whatever the leaving group is, it could be a chlorine, could be an iodine, it could be a tosylate that we'll look at later on. As long as they're anti to each other, that's the requirement for the elimination to occur. Now, I mean, this is the kind of thing that I spend a lot of time, or I've spent a lot of time in the past, you know, trying to explain to my students, going from here to here, drawing everything in the correct way. But I mean, here's, you know, the way you can think about it. If I look at my Newman projection, remember that this is a carbon, right here, that's a carbon, and then this circle is also a carbon, right? That's the second carbon. So you see that you have, I'll call this one C1 and I'll call this one C2. So I've got C1, then I'm going to form a double bond up to C2, like that. Well, what's on C1? I've got a methyl on the left-hand side. I've got a phenyl on the right-hand side. What's on C2? I've got a tert-butyl up here. So I've got a tert-butyl group up here, and I've got a hydrogen over here, like that. So that is the product that you would get. It's the same thing that's drawn here. I just drew it a different way, right? If you flipped it, you know, if you drew an axis right here and you flipped it 180 degrees, you'd end up with this. It's the same thing. Okay, so that is how you recognize, you know, or determine whether you get the E or the Z product. So again, it's got to be anti-coplanar. Now let me talk about this a little more. So the whole thing about having a 180-degree angle, that's actually not perfectly required for an E2 mechanism. So what it means is this. If you look at this Newman projection, it's right here. I mean, it looks to me like the bond angle here is 180 degrees perfectly, but it's not. It's actually more like around 180. It can be 178, 179, and you're like, who took the time to measure this? Well, it wasn't me, but anyhow, I guess it says here anywhere between 175 and 179, it's going to work. So instead of being anti-coplanar, which would be exactly 180, we call it anti-periplanar, okay? And that's the term that I will use, is that the hydrogen and the leaving group have to be anti-periplanar. Now, again, you know, if you think about E and Z products, you know, you can't just go off of, you know, sterics and say, well, the E is going to be more stable because it's usually less sterically hindered, okay? But in order for the molecule, or sorry, how should I phrase this? If the molecule has to adopt an anti-periplanar transition state, we get Z isomers all the time. So we get all kinds of isomers that you're like, oh, that wouldn't be the preferred isomer, but as long as the molecule can adopt that anti-periplanar transition state, or when it does, that dictates what the product is going to be. Okay, so with that in mind, let's take a look at these two examples, so it says, assuming that they both proceed through an anti-periplanar transition state, predict the products for the following reaction. Well, look, you can see we're going to start with this one. I've got my base. I'm going to put a lone pair here, and I'm going to draw the curved arrow. So I'm going to pull off this proton, make a double bond, and then lose the leaving group. So I'm going to form a carbon-carbon double bond like that. So I know I've got that much, but if I take a look at the R groups, you see how the two R groups in blue, they're both going back, right? So that means that they're going to be on the same side of the molecule. So I'm going to put R2 and R2 over here like that, okay? You see that how R1 and R1 are both pointing out towards you, right? So that means that they're going to be on the same face of the molecule like that. So R1 and R1. So that's going to be the product. Now, if you're thinking, hold on, you didn't draw a Newman projection. What the hell's happening here? No, I didn't, because I wanted to show you without drawing a Newman projection first that the answer can be, correctly determined without drawing a Newman projection. Why? Because you can see that all of the atoms required are in the same plane. So you can also do it drawing a Newman projection. Let me show you how to do that. If your eyeball, let's say, was looking down the carbon-carbon bond, let me erase some of the spinach I got here. What would you see? Okay, so I'm going to draw the Newman projection right here. Where's my pen? So I've got a carbon in the front, right? And I'm talking about this carbon right here. I've got the hydrogen pointing straight down. I've got R2 going off to the left. I've got R1 on the right. For the carbon in back, that's the big circle. I've got the bromine, anti-periplanar. Then I've got a bond here and a bond here. And you can see that the R2 is down and to the left, and R1 is down and to the right. So if I eliminate this bromine and this hydrogen, when I form my carbon-carbon double bond, you can see that the two R2 groups are going to be on the same side of the double bond like they are here. And you can see that the two R1 groups are going to be on the same side of the double bond. So either way works. You can either draw a Newman projection if you want, or you could just draw it. You can just draw it like this, so that you can see all the dashes and wedges. Make sure that everything that is going to be eliminated, the hydrogen and the bromine, are anti-periplanar or coplanar. And there you go. Give me a thumbs up if you follow me on that one. Everybody, this is a really important question. I'm definitely going to ask it on your next quiz, something like it. Okay, I'll give you at least one question, or I ask you, this, you're going to get a stereospecific reaction here, and you have to evaluate, is it the E or the Z? Well, you can probably guess where we're going with this, and I'll go over the next one a little bit quicker. But let's start with the Newman projection first on this one. Let's start with the Newman projection first. So what would I see? If I look down here, I've got my carbon in the back, I've got my carbon in the front, my hydrogen is going down. I've got my R2 group over here. I've got my R1 group here. The other one, I've got the bromine. It's anti-periplanar. But when I look at these two bonds, son of a gun, could draw a straighter line than that. There we go. Anyhow, now I've got the R1 down here, and I've got the R2 over here. So when I form my carbon-carbon double bond, you can see that I'm going to have the R2 and the R1. So I'm going to draw it like this time. Okay, so we'll call this C1. So if this is C1, I've got R2 here. I've got R1 here. And if this is C2, the other one, this is C2 up here. I've got R1 over here, and I've got R2 over there. There you go, my friends. That's it. And we'll look at another example of that today at some point. But there you go, a stereospecific elimination reaction. Not the simplest thing that we look at in the class, definitely not, but very important that you're able to draw the correct stereoisomer that results from a stereospecific E2 reaction. Well, let's move on from there. So if you take a look at this example here, so follow along with me carefully. This requires some thought. If you look at this beta hydrogen in this molecule, you see how instead of one proton, it's got a couple of protons? Well, whenever you have a couple of protons, and I alluded to this earlier today, then there's two rotamers. where these hydrogen, you can have one rotamer where this is antiperiplanar, and you obviously have this one where this hydrogen is antiperiplanar. Well, when you have that, you end up with the E and the Z. Okay, you end up with both stereoisomers. So in this case, we say the reaction is stereoselective, but it's not stereospecific. Okay, you might end up with a major and minor product in this case, but it's not stereospecific. You're going to end up with two products at least. All right, there you go. So again, the whole idea of stereospecificity, of having to draw a Newman projection and all that stuff, that only happens when both the alpha and beta carbons are stereocenters, right? And if you don't believe me, go back here. You see that this is a stereocenter, this is a stereocenter, so is this, so is this. If we go back, where was our example? You see that this is a stereocenter, this is a stereocenter. So that's when you have to worry about stereospecificity. If you're struggling with the words, you're like, this is annoying, you know, like a stereospecific and stereoselective. Well, if you think about stereoselective, right? Let's say you're going to, what's a place I like to go? Maybe a donut shop or something. You know, if I'm selective for one over another, that means, you know, I'm going to get more of this donut versus that donut, right? You know, you want the, I don't know, whatever donut you like more than another. You want the one with the frosting or something, right? So that's selective. Whereas stereospecific, a stereospecific means the substrate is only going to give you one product. That's it, one possible product. And that's the thing where you have to do the whole Newman projection treatment in order to determine what the actual product is. Okay, so if you understood the concept of antiperiplanar, sorry, I didn't see the question. Okay. Anyhow, thanks for his student answering for me. Sorry, my chat's a little laggy here. Anyhow, if you understood what was going on when I was mentioning the requirement of something being antiperiplanar, okay. The next thing that we're going to look at is we're going to talk about it with respect to a cyclohexane ring. So before we do that, I want to take a look at some examples. So this is a specific example. This is question 7.21. So just give me a second here and we'll take a look at these. You can start taking a look. It says predict the major and minor products for these, you know, different E2 reaction that would occur with these substrates. All right, so we're going to start with A. Now, if we look at A, we see that this is not a stereocenter, is it? Right, here we have our alpha carbon, okay? But on this beta carbon, there's no hydrogen, so I'll just forget about that one. But here we have two hydrogens, right? If there's two hydrogens, what does that mean? It means I'm going to get a mixture of E and Z, depending on which one of these protons I rip off. Now, in terms of the reaction being stereoselective, what are we going to get? Is their major product? We're going to get the one that produces the least hindered or the least sterically strained alkene. Is going to be the preferred, you know, product. So I'm just going to draw a mechanism just because. Okay, so if I take a base, I'll just write base, so it's pretty generic. Okay, it might be ethoxide. It's going to pull off this proton, form the double bond. We get the loss of the leaving group. But again, since this is not a stereo center, this reaction is going to be stereoselective. Stereoselective. And so I'm going to end up with, let me use my black pen. I'm going to end up with both the E and the Z product. So I could have this, okay, like this. So this is the E product. And then I could also get the Z product. So let's draw the Z product. So I have my double bond like this. So I have the E product and the Z product. Could anybody predict which one of these would be the major product in this stereoselective reaction? And it's not a trick. Would it be the E or the Z? What do you think? Which one would be the least sterically hindered? Yeah, it's definitely going to be the E, isn't it? Right? So this would be the major, oops, here's my pen. This would be the major product, and this would be the minor product. And again, it's just based off of sterics. You can see how if the base has the option of pulling off either proton, well, the transition state that's going to lead to this, it's going to be way less sterically hindered than this. I mean, if any of you have a model kit, You could try making a model of this, and you'll see how annoying it is to try to put a phenyl right next to a tert butyl. They keep crowding each other, and the models start clanking together and everything. Okay, well, let's take a look at B. And B is going to be a stereospecific reaction. How do I know? Because the alpha carbon is a stereocenter. This beta carbon, I don't have to think about it because there's no protons, but this beta carbon is a stereocenter too. Right? If I have two stereocenters, then I have a stereospecific reaction. So let's draw in the proton. And you can see that the way that this is written, that the bromine and the proton are not anticoplanar, are they? They're not anticoplanar at all. So why don't we draw a Newman projection for this compound? So what I'm going to do is I'm going to draw a Newman projection. I'm going to run out of space too. But I'm going to draw a Newman projection of what I see when I look down this carbon-carbon bond. Okay? I'm going to go a little quicker, but what you would see is something like this. So you'd have the phenyl up here. I'll just write pH for phenyl. You have the hydrogen coming down into the left. You have the methyl group coming down into the right. I'll write Me for methyl. What else? In the bottom, you have the tert butyl group pointing straight down. If you've got the proton like this, then that means on this side, on the left-hand side, you've got the bromine. Okay. And then over here, you've got the hydrogen. Give me a thumbs up if you follow me on just drawing the Newman projection. So far, so good kind of thing. Cha, is everybody with me on that? Just drawing the Newman projection. We haven't drawn a product yet. We're not there. We're still working on that. Okay, well, if the proton and the bromine are not antiperiplanar, what do I have to do in order to render them antiperiplanar? What can I do? Could anybody answer that? And I'm not looking for a long answer. Just, what's the simplest thing I could do? And if you might even think, oh, come on, Mr. Dion, that's a ridiculous question. But just what would I do? I'm stuck because they're not anticoplanar. Does anybody have an idea? We could take a class vote or something. Like what would I do now? They're not antiperiplanar. Am I stuck? Am I in trouble? What would I do? Well, the good news is that there's free rotation around the carbon-carbon sigma bond, the one where the pi bond is going to be formed, right? So all I have to do is rotate either the bromine. I can rotate the bromine over here, okay? Or I can rotate the hydrogen over here. Either way, it doesn't matter. I'm going to rotate the hydrogen counterclockwise 60 degrees. So that means that I have to rotate the methyl and the phenyl counterclockwise 60 degrees. So if I do that, or sorry, did I say 60? I meant 120 degrees. Anyhow, so I'm going to rotate it 120 degrees counterclockwise. And then what would I end up with? Well, let's draw it. So it's going to look like this, this. Now my hydrogen is going to be over here. My methyl group is going to be up here, and my phenyl group is going to be up there. My bromine, I didn't do diddly squat with that. My hydrogen remains unchanged. And my tert butyl group is still here. Okay, there we go. So now you can see, where's my yellow pen? There we go. Now you can see that the bromine and the hydrogen are antiperiplanar. Boom, we did it. Awesome. So now you can see what's on the same side of the double bond. You can see that the phenyl and the tert butyl are on the same side of the double bond, and so are the methyl and the hydrogen. Right, so let's draw what it's going to look like, and you can take whatever hammer and tongs approach you need. You just need to get the right answer, right? So let's draw C1. We'll draw a double bond up to C2. C2. We'll call this one, that's C2, okay? So let's see. On C1, we've got a phenyl on this side. We've got a methyl over here. And on C2, we've got a tert butyl group up here. And we've got a hydrogen over here, like that. And there you have it. So the phenyl and the tert butyl are on the same side, and the hydrogen and the methyl are on the same side. Now, is that an E or a Z product? This is actually a Z product, isn't it? Okay, this is zusammen. Okay, so this is the product. Okay, in the book, I mean, I don't have the book open or anything, and I don't look at the solutions manual a whole lot, but they probably write it a little cleaner than that. They might write it like neat and tidy, like this, where you have, you know, the methyl and the phenyl down here, and then you have the hydrogen and the tert-butyl here. But either way, it's the same thing. There we go. The goal is not to remain unhindered, not at all. That's only in a stereoselective reaction, right? If we go back to the first question, right, the goal here was to remain unhindered, right? Was to avoid making this compound. Why? Because this is a stereoselective reaction, right? If we go back here, stereoselective means you're going to get a major and a minor product. When we're dealing with a stereospecific reaction, we're only going to get one product, right? And in a stereospecific reaction, that results when we have both carbons as being chiral. You can see how this is not a chiral carbon, and so this is a stereoselective reaction, whereas here we have a chiral carbon here and a chiral carbon here, and so this reaction is stereospecific. Stereospecific. All right, so we only get one product here. If you go back in the notes, here it says, where is it? Okay, it says it right here. It says that although the E isomer is usually more stable, right, the one that is less sterically hindered, but in order for us to meet that requirement for that anti-coplanar or anti-periplanar transition state, we see many examples like the one that we're looking at now where we end up with the Z isomer. Even though it's less stable, it's the only one that's going to be formed. All right, does that help? All right. Anyhow, so why don't we hold off on 7.21c? We'll skip that one for now. And then if we have time, we'll come back and we'll take a look at 7.21c. I'll make a note of that, and you can remind me if I lose my note. Anyhow, so now we want to take what we've learned about the anti-periplanar requirement for an E2 reaction to occur. We want to take it, and we're going to take a look at what happens if we try to do an E2 reaction on a cyclohexane that has a good leaving group. Okay, so now we're going to look at six-membered rings. So consider what happens if you try to do a dehydrohalogenation on a cyclohexane derivative. Well, if I look at the Newman projection, okay, of this molecule, so this is chlorocyclohexane, you can see that in order for an elimination to occur, check this out, the chlorine has to be in the axial position. Now, I know that that is not the preferred conformation, right? You have this conformation where the chlorine is axial or equatorial. The one that's equatorial is present in a larger amount. However, an E2 elimination cannot occur when the chlorine is equatorial. Why? Because when the chlorine is axial, I meet the requirement of having a hydrogen anti-periplanar to it, whereas when the chlorine or any leaving group is equatorial, there are no protons that are anti-periplanar to it, and therefore an elimination will not occur. So the bottom line is this: what we're going to see is that elimination can only occur when your leaving group is axial. Okay, so an E2 elimination can occur when your leaving group is axial, and an E2 elimination cannot occur when your leaving group is equatorial. Okay, so, and again, I'm repeating myself. In order for the elimination to occur, the leaving group has to be axial, and of course the proton that is anti-periplanar to it would also be axial. All right, if you take a look here, I mean, where are the axial protons with respect to this chlorine? If this is your alpha carbon here, you've got a beta carbon here, and you've got a beta carbon over here. Well, the beta carbon in blue has a proton going down. That would be anti-periplanar to the chlorine. And the beta carbon in green also has a hydrogen that is anti-periplanar. So there's actually two hydrogens that are anti-periplanar to my chlorine. All right. Well, let's move on from there. So if I take a look at these two molecules, if I call them A and B, it says which of the two molecules will not be able to undergo an E2 elimination and why? Could anybody answer this? You know, seeing as in order for an elimination to occur, both the hydrogen and the chlorine have to be axial. Could anybody tell me which one of these will not undergo any E2 elimination whatsoever? Would it be A or B? One of these won't do diddly squat if you treat it with a base. It's going to be B that will not undergo an elimination, right? Remember the axial and equatorial alternate, right? If everything's pointing up. So if the chlorine here is up and axial, right? That means that, and this is the alpha carbon, I've got a beta carbon here and a beta carbon here. If this hydrogen is pointing up, it's up and equatorial, right? And remember that the requirement would be that the hydrogen also has to be axial and it would have to be pointing down, right? So this one is up and equatorial. So you're going to get no elimination whatsoever. Whereas if you look at the first one, again, if our chlorine is up and axial, well, if this hydrogen is going down, remember the axial alternates, up axial, down axial, etc. So that means that this is pointing down and is axial, as is this one. This one is down and axial. So that means that the requirement is fulfilled and this one can undergo elimination. So we'll put here yes and no, okay? If you need to draw a chair, if that would help, we could draw a chair. So let's draw one that looks like this, like that. Okay, if our chlorine is up and axial, we have a methyl group that's going up and equatorial. We have another methyl group that's going up and equatorial, like that. Oops. Son of a gun, what's wrong with my chair? No, I had it right the first time. Sorry, my chair's just drawing a little funny there. But anyhow, so you have a methyl group going like that. So that means we've got a hydrogen going down in axial, and we have another hydrogen. I'll try to break the bond here so that it looks like it's going behind the page. I have another hydrogen. Son of a gun. Sorry, my iPad is not being cooperative. Where was I? Oh, shit. All right, well, let's start drawing the chair again. So if I draw chair like this, I have the chlorine going up like this. I have a methyl going up in equatorial. I have another one going up in equatorial like this. So these are the methyl groups. Okay, so that means I have a hydrogen going down an axial, and I have another hydrogen going down an axial. And so this will, yes, undergo an E2 elimination. Whereas this one here, if I draw the chair again, chair, okay, I have a chlorine going up an axial. I have the methyl groups going down an axial. And then my hydrogens are up in equatorial, like this. There we go. And so they are not anti-periplanar, right? The requirement is met here. You can see how this is anti-periplanar, as is this one, where the other one, none of the hydrogens are anti-periplanar. All right. So there you go. So we can just look at a compound now without even drawing a chair and just knowing how the hydrogens and the groups are arranged. It says here, rationalize the products formed in the following two reactions. So if we take this compound where the tert-butyl and the chlorine are trans to each other, and then this compound where the tert-butyl and the chlorine are cis to one another, if you see this one, it says the E2 reaction is slow, and you only get one product, whereas the second one, the E2 reaction is fast, and you get two products. Now let's see if we can rationalize this. If this chlorine, okay, if this chlorine is pointing down and axial, how would this tert-butyl group be pointing? Could anybody tell me? Up, down, sideways, axial, equatorial, something else? And it's not a trick question. It's going to be going up an axial. Absolutely, yes, 100%. So Kelly and Mackenzie, both 100% correct. It's going to be going up and axial. So let's think about this for a second. The chlorine is great, okay, if it's going down an axial, but that means that a tert-butyl group, which is really big and bulky, I mean, it's huge. It's going up an axial. It's got 1,3 diaxial interactions. So that means that this molecule has to be in a really disfavored conformation in order for the chlorine to be axial, right? You've got a big old tert-butyl group that's got to be axial. Well, you're not going to eliminate this proton that I'm putting in red. That's impossible because it's pointing down and equatorial. And if it's not axial, because this is axial, if this is equatorial, there's no elimination going to occur, right? The only proton where elimination could occur is going to be with this one here that's pointing up, okay, with this hydrogen, because it's going to be up and axial. So that means the elimination is going to occur here to make this double bond, and that's going to be the only product. You know, there's not a lot of room on here, but if I try to draw a chair like this, okay, to show you, you know, what's this going to look like? If my chlorine is going down an axial, then my tert-butyl group is going up and axial, right? This hydrogen is going down, but is equatorial, so that's not going to work. The only one that's going to work is the one that's going up and axial, which is this one here, all right? Now, if I take a look at the next one, the reason why this one is going to go so fast is because if this chlorine is up and axial, that means that the tert-butyl group is now up and equatorial. So the conformation is much more favored. If I draw the chair, and again, there's not a ton of room here, but if I draw the chair, then I've got my chlorine, you know, and I'll just draw the conformation that's going to react. So since I'm kind of running out of space, this is the conformation that's going to react. So if my chlorine is going up and is axial, that means that my tert-butyl group is up and equatorial, which again is much more favored. I've got a hydrogen going down an axial here. I've got another one going down an axial here. So that means the proton that I'm writing in blue here, that one can be abstracted to make this product. And then the hydrogen that's going down here, right, which would be this one, okay, and the blue one will be this one. The one that's in green can be abstracted to make this product, okay? So that's the rationale. And this is why you need to really kind of think your way through these problems. You know, there's no just easy answer, you know, A gives me B and that's it, all right? So you see that the first one is more selective. You only get one product, but the product is much higher, or the reactant, the starting material is in a much higher conformation since you have the 1,3 diaxial interactions, right? Here, you know, and here, okay? Whereas they're not present with the tert-butyl group in the second compound in its conformation. And you can see that our textbook has all kinds of questions like this in the same vein where it kind of helps you understand what's going on. And I even put this example in the notes, the one with menthol and neomenthol chlorides. We'll take a look at that if we have time. But again, there's all kinds of good questions in our book where it gets you to evaluate, you know, will this elimination occur, will it not? So, you know, we looked at a lot of different things in section 7.8 when we're talking about E2 reactions. There's just a lot of material, you know, and there's a lot of things that we have to take into account when we're predicting products, right? Is the reaction going to be stereospecific, right? Do we have two chiral centers, or is it going to be stereoselective? Okay, so that's something to think about. Stereospecific, you'd only get one product. Stereoselective means you're going to get major and minor products. There we go. So we looked at that. And again, the only way to master this is to do lots of practice. Okay, and this comes out of the mouth of David Klein. Okay, it's really the only way to master it. There's no quick answer in organic chemistry that you just, you know, do this and say this 10 times and then you're going to know everything. Well, it's really tough to do it that way. Let's take a quick peek at this example. I'm not going to draw the chairs on this one. I just want to see if we can rationalize it based on our knowledge of up and axial and down, and right, that kind of stuff. So it says when menthol chloride, this compound here, is treated with a strong base, you only get one product. Yet when neomenthol chloride is treated with a strong base, you get two products. I'm going to answer this as quickly as I can. If this chlorine, right, in menthol chloride, it says it only gives us one product. If it is down, In order for it to be eliminated, it has to be down and axial. Well, let's take a look at this beta carbon, and let's take a look at this beta carbon. So the one that I have here in red, if the hydrogen is going down, that means it's down and equatorial. So no elimination will occur. You will not get a double bond here. Whereas the one that I'm labeling in blue, if this proton is going up, it's up and axial, right? Because down axial, up axial, down axial, up axial. That means I can get an elimination occurring here, and I can make a double bond right there. So the only product that I'm going to get would be this, where I have my 6-membered ring. I formed a new double bond right here. I didn't touch this stereocenter at all, and I didn't touch this stereocenter, didn't even think about it. Okay, give me a thumbs up if you follow me on that one, because if you do, then the fact that neomethyl chloride makes 2 products is going to be, you know, I would think maybe not abundantly clear, but it'll be pretty clear. Okay, all right, cool, great, awesome. Well, let's take a quick peek here. So we've got the chlorine, and again, we're just assuming, because if you're going, well, Mr. Dion, how do you know this is up and axial? It can be both. It can be up and axial. It could be up and equatorial. There's 2 conformations, but we're talking about elimination reactions here. So the only way we can do an elimination is if the chlorine is up and axial. So to heck with the other conformation. I don't care about it. I'm not interested in it whatsoever. In order for the elimination to occur, it's got to be up and axial. Well, if you take a look at this proton that I'm writing in green here, okay, it is down and axial. So that means I could form a double bond here, right? Which would give me this product. Let's draw it out. It would look like this. I have a double bond here. I didn't do diddly squat with this methyl group. Now this is an sp2 hybridized carbon, so there's no stereocenter here. Well, I could also pull off this proton that's pointing down, couldn't I? Because it's down and axial, just like the one in green, but it's going to produce a regioisomer where I form a double bond here. Let's draw what that looks like. We draw our 6-membered ring, comme ça, as we say in French. All right. We have the double bond. We have the methyl group. Again, we didn't touch it. It's still on a wedge, or sorry, a dash. And then we have the isopropyl group, which we didn't touch either. And there you go. All right. That's all there is to it. All right. And you can be guaranteed that this is going to come up on the quiz. And this kind of question, like your understanding of the relative position of a leaving group on a 6-membered ring, on a cyclohexane ring, and the proton being anti-coplanar, your knowledge of this requirement will always be tested on a standardized test in organic chemistry. So again, if any of you are taking an MCAT exam, for example, this is the kind of thing that they would expect you to understand, is the relative positioning and the requirement of the requirements for an E2 reaction. In fact, a number of years ago, I think it was maybe 4 years ago, they made a big change to the MCAT exam, and they changed it so that it didn't have as much organic chemistry and it had more biochemistry on it. And actually, one of my former students who got into medical school less than 6 months ago, he told me after he came out of the exam, he came to see me and he's like, you wouldn't believe how much organic chemistry was on the exam. So maybe they've changed it again, unbeknownst to anybody. Anyhow, let's take a look at this one. It just says predict the major and minor products that you would get from these E2 reactions. Look, we've got a tertiary alkyl halide. We've got an unhindered base. Okay, unhindered base. I mean, they're telling us it's going to be an E2 reaction. This is our alpha carbon, but there's 2 types of beta carbons, aren't there? Right? I have this beta carbon that I'm going to write a blue B next to, so that's got a proton on it. And then I also have these 2 beta carbons, which are identical because this isn't a stereocenter. I'll just choose this one here, and there's a proton here. So my unhindered base, could you tell me which one of these protons it's going to remove preferentially? Would it be the blue one or the green one? And it's not a trick. Which one would give the major product? If it's an unhindered base. So I see the carbon in blue, right? the carbon in blue is less hindered, right? Because it's just kind of hanging out there, okay? It's only attached to one more carbon, whereas the carbon in green is more sterically hindered, right? It's attached to 2 carbons, right? So since I have an unhindered base, it's going to rip off the proton that's going to give the most stable product. This one is more sterically hindered, right? It's harder to grab, but since this is unhindered, it's going to go for that proton to give you the Zaitsev product. So the major product that you would get would be 6-membered ring, double bond, and there we go. So this would be our major product. Okay, this is the Zaitsev product, Zaitsev, all right? Whereas with an unhindered base, this is the low-hanging fruit, right? That's the easiest one to grab. It's on a primary carbon, okay? But it's going to give us a less stable product. So we're going to get this, and then we're going to end up with this compound as well. This is methylene cyclohexene. This would be the minor product, and this is the Hoffman product. Okay, there we go. So again, how do you solve a problem like this? If I just erase everything on here, okay, I've got my alpha carbon. That's the one the iodine is attached to. I look at the 2 beta carbons. I've got this beta carbon, and I've got this beta carbon. Maybe I should be consistent with my colors here, okay? I've got this beta carbon. You draw one product that has the double bond between this alpha and beta. You draw the other product, which has the double bond between this alpha and beta. You look at the substitution. This double bond, right? Could anybody tell me what the substitution of this double bond is that I have the black circle around? Is that mono substituted, di substituted, tri substituted, tetra substituted? What would the substitution of this double bond be? Because in order for us to know that this is the major product, we have to understand substitution. It's tri-substituted, right? Because I look at the double bond, how many carbons are attached to the 2 carbons in the double bond? Let's count. We've got the double bond, we've got 1, 2, 3 carbons attached to the double bond. If I look over here, here's my double bond. I've got only 1, 2 carbons attached to my double bond, right? Here there's a hydrogen, here there's 2 hydrogens. So this one is tri-substituted, okay? And this one is di-substituted. And remember that last class we talked about how the more substitution we have in a double bond, the more stable it becomes. All right, so the Zaitsev product is the most stable product. It's the tri-substituted product, and there you have it. Okay, the next one, we have a hindered base. We're using potassium T-butoxide. So this is a hindered base. We'll take a look at our alpha carbon here. Okay, let me zoom in a little bit. Okay, we have our alpha carbon. We've got 1 beta carbon here, and we've got a beta carbon here. If this bromine is going up and axial, so if this is, let's say, let me use a black pen. If this is up and axial, that means that this proton here, maybe I should write it in blue, that this proton here is going what? Down, down, and is also axial. And that also means that this proton is going down, down, and axial. So I've got 2 possible regioisomers here, don't I? Right? I can form a double bond between this alpha and beta carbon, and then I can form a double bond between this alpha and beta carbon. Let's write out the 2 products that you'd get. First, we'll start with abstraction of the proton in blue. That would give you this. So we'd have this product where we have a double bond here. We have the methyl group, and that's it. All right. Then we would also get the product that results from the abstraction of the proton in green. So we'd have our 6-membered ring. We have the double bond here, and then this is going to still be a wedge like that. Could anybody tell me, since I'm using a hindered base, right? This is a hindered base. Could anybody tell me which one of these would be the major product? Would it be the one in blue or the one in green if I'm using a hindered base? It's going to be the one in green, isn't it? Right? Even though the one in green is only di substituted, it's still going to be the major product. Okay, this is going to be my major product. Why? Because the hindered base is going to go for the proton that is less hindered, right? This one is attached to a carbon that has 1, 2, 3 carbons attached to it, whereas the other beta carbon only has 1, 2 carbons attached to it. Remember, a hindered base like T-butoxide is really big. It's always going to go for the low-hanging fruit, okay, so to speak. So this would be our major product, and then this would be our minor product. So here the minor product is actually the Zaitsev product, and the major product is the Hoffman product. Take a look at the last one. If we examine the cyclohexane, so this bromine, let's say it's going up and axial. So that means that this methyl is going down and axial. That would mean that this proton here is up and equatorial. So it's not going to be eliminated. Sorry, I should write a hydrogen there. But nothing is going to happen there. So we can eliminate that. But if I have a proton going down here, which I do, I have one going up, but I only care about the one going down because it is down and it is also axial. So the only elimination that's going to occur would be right here to form the double bond there. And the only product I would get would be this, where I have my double bond here, and my methyl group wasn't touched at all. So this is the only product. Nothing else. So there you go. So now you can see that when you're predicting the products of an E2 reaction, it does require some thought. You really have to think about everything that you've learned and decide, is this a stereospecific reaction? Is it stereoselective? What type of base do I have? Is it hindered? Is it unhindered? And later on in this chapter, you're going to see that we're going to look at figures like 7.20. And then we also have some other tables in section 7.11 where we're actually going to really spend some time honing in on what's the decisions that you have to make, and how do you make them when you're trying to decide what the products would be of an elimination or a substitution reaction.